So we're going to continue looking at integration by parts. In the last video, you learned the basic formula and saw how to apply it. Remember that the whole point is we're going to end up integrating u times dv, and that's going to equal u times v minus the integral of v du. And we set up every problem with that little chart that I would write on the side, and we would do this times this minus the integral of that times that, and all that stuff. There are a couple variations on integration by parts that I need to show you. And today we're going to look at 3 specific variations, and in the final video you're going to watch, you're going to look at one other variation. So a couple variations. First example, I would like to do the integral of the natural log of x dx. The integral of the natural log of x dx. First of all, the answer is not 1 over x plus a constant. You're thinking derivatives if you were about to say that rather than integrals. We never learned how to integrate the natural log of x. However, integration by parts can be used to give us a formula for this. Here's how I can do this. This natural log of x dx thing, I can actually say that that's a product. And I can say that one part is dx, and the other, one part is the natural log of x, and the other part is dx, or if you'd prefer, we could say 1 dx. L-I-A-T-E, I have something logarithmic, and that 1 dx, I can call that algebraic. I'm going to make u the natural log of x, and I'm going to make dv 1 dx. Okay, so I'm going to go and I'm going to find the derivative of u, derivative of the natural log of x, is 1 over x dx. The integral of 1 dx, well, that's just x. Using my formula, u times v minus the integral of v du, this is going to give me, let's see, I've got x times the natural log of x minus the integral of x times 1 over x dx. Well, I can simplify that. X times 1 over x is just 1. So this is x times the natural log of x minus the integral of 1 dx. I can go and integrate that, and I've got x times the natural log of x minus x plus a constant. And this is the formula for the integral of the natural log of x. I don't think this would be a formula you would need to memorize, but what you would need to know is where it comes from. You can create this formula by using integration by parts. Well, there's some other things that we looked at where we were able to find derivatives of that particular function, but not an integral. Integration by parts can help us get around those things. For example, let's do an inverse trig problem. The integral of the arc cosine of x dx. L-I-A-T-E. I'm going to use the same trick as in the last problem. I've got my arc cosine x and a 1 dx. I'm going to call my arc cosine function an inverse trig piece, and my 1 dx as something algebraic. I can say that u equals the arc cosine of x, and dv is 1 dx. Du, the derivative of arc cosine x. Well, here's where you may need to go back through that salmon-colored packet to the table of derivatives, or look back in your notes to section 5.8. I know it's been a little while since we've done derivatives of this one. But hopefully, you can find that the derivative of the arc cosine of x is negative 1 over the square root of 1 minus x squared dx. As for my v, what's the integral of 1 dx? Well, just x, like it was last time. We can now do u times v minus the integral of v du. Okay, this is x times the arc cosine of x minus the integral of this thing times that thing, negative x, over the square root of 1 minus x squared dx. Well, why don't I clean this up a little bit and do away with those double negatives, and I can call this x times the arc cosine of x, just plus the integral of x over the square root of 1 minus x squared dx. And this isn't quite as easy an integral as the one I got in the previous problem, where I was just integrating 1. Well, to integrate this, we go back to our standard trick for integration. We need to go use a U substitution. I'm going to make U 1 minus x squared, and I'm going to make du negative 2x dx. I'll stick a negative 2 inside, a negative 1/2 outside, and I can turn this problem into, let me move up a little bit, I can turn this problem into x times the arc cosine of x minus 1/2 times the integral of du over the square root of u. Well, I'm going to rewrite that so I can then just use power rule on that thing. X times the arc cosine of x minus 1/2 times the integral of u to the negative 1/2 du. Go and integrate. I get x times the arc cosine of x minus 1/2 times u to the 1/2 over 1/2 plus a constant. 1/2 times the reciprocal of this is 2. Those pieces are going to cancel. I'm going to replace the u with what it stood for, and I'm going to get x times the arc cosine of x minus the square root of 1 minus x squared plus a constant. And there's my formula. You would do something similar to create a formula for the integral of the arc sine of x, the arc tangent of x, the arc cotangent of x, and you'll see some of those in the homework. The next variation that we need to look at is what happens if you're given a definite integral, if you're asked to find an area under a curve. For example, the integral from 0 to pi over 2 of x times the cosine of 2x dx. Well, it looks like an integration by parts problem, because I've got x times the cosine of 2x, and the stuff inside my cosine, its derivative isn't really based on x, so I can't use that. So I'm going to go do my integration by parts, and I'm going to sort of ignore the limits of integration for right now. LIATE, that's something algebraic and something trig. I'm going to make my u x, and I'm going to make my dv the cosine of 2x dx. So du should be pretty easy. Derivative of x is just 1 dx. V is going to take a little bit of work. I need to do the integral of the cosine of 2x dx. Well, this integral itself is going to require U substitution. I kind of don't want to use the letter U because I already have U standing for other things over here. How about like a W substitution? I'm going to say W equals 2x. dw equals 2 dx. Stick a 2 in and a 1/2 out. I'm going to get v equals 1/2 times the integral of the cosine of w dw. So I'm going to get 1/2 times the sine of w, or 1/2 times the sine of 2x. So I can now say u times v minus the integral of v du. This is going to give me, again, I'm going to ignore the limits of integration for right now. I'm going to get, let's see, 1/2 times x times the sine of 2x minus, let's see, minus the integral of 1/2 sine 2x dx. Outside the brackets then, I'll put my 0 and my pi over 2. Oh goodness. Okay, so over here, why don't I start by just moving that 1/2 up front. 1/2 x sine 2x minus 1/2 times the integral of the sine of 2x dx. Looks like another U substitution problem. but at least this integral is just U substitution, as opposed to the original one, which was integration by parts. U is going to equal 2x. Du is going to equal 2 dx. So my 2 in and another 1/2 out front. Move up again. This is going to give me 1/2 x times the sine of 2x minus 1/4 times the integral of the sine of u du, 0 to pi over 2. Okay, well the integral of sine is negative cosine, 1/2 x times the sine of 2x, minus, actually not minus, we're going to say plus because of the double negatives that we're getting, the cosine of u, 0 to pi over 2. But the 0 and pi over 2, those are x values, so I want just x's in my answer. And I'm going to get 1/2 x sine 2x plus 1/4 cosine 2x, and I'm dealing with this between 0 and pi over 2. So I'm done with my antiderivative work. Now I'm going to go and I'm going to plug in those limits of integration. This is going to give me 1/2 times pi over 2 times the sine of 2 times pi over 2, well 2 times pi over 2 is just pi, plus 1/4 times the cosine of, again 2 times pi over 2 is just pi, minus, go and plug in your 0, 1/2 times 0, sine 0, plus 1/4 times the cosine of 0. Okay, so pi over 4 times the sine of pi, that's just 0, plus 1/4 times the cosine of pi, that's a negative 1, minus, let's see, 1/2 times 0 times the sine of 0, that's just 0, minus 1/4 times the cosine of 0, well cosine of 0 is 1, we're going to get negative 1/4 minus 1/4, that looks like negative 2/4, and we've got a final answer here of negative 1/2. There's one more variation that I want to show you, which is a little involved. I'm going to give a name to this variation a little bit later, but I first need to show you how this works, and I'm going to give you a total of 2 examples of this. So I want to integrate e to the x times the sine of x dx. So L-I-A-T-E, I have something trig, and I have something exponential. Okay, so my u is going to equal the sine of x, dv then is e to the x dx, du, the derivative of the sine of x, is cosine x dx. The integral of e to the x dx is just e to the x. So I'm going to get sine x e to the x minus the integral of e to the x cosine x. And I'm going to say, I'm just going to rewrite the original problem here. The integral of e to the x sine x dx is going to equal e to the x sine x minus the integral of e to the x cosine x dx. Well, we saw something like this in the last video where I still have a product over here. I need to go use integration by parts again. So I will. L-I-A-T-E. I've got trig and I've got something exponential. I'm going to say that u is the cosine of x. My dv is e to the x dx. Derivative of the cosine of x is negative sine x dx. Integral of e to the x dx is e to the x. So u times v minus the integral of v du. We come over here. Again, I'm just going to rewrite the original problem. Integral of e to the x sine x dx equals. Okay, so e to the x sine x minus. Okay, so e to the x cosine x minus the integral of e to the x times negative sine x. You know what, forget that minus integral. Why don't I just say plus the integral of e to the x sine x dx. Okay, you know what, let me go distribute the negative and then we'll try to make some sense out of this. Got the integral of e to the x sine x dx equals e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. So integration by parts again, but it's just going to keep happening. I'm going to keep getting integration by parts integrals, and it's never going to end. First of all, to give a name to what I have happening here, I'm going to call this a cyclical integral. Because it just keeps like cycling through e to the x sine x, and e to the x cosine x, and e to the x sine x, e to the x cosine x. It's never going to end. Cyclical integrals occur when you have something in the form t and e, something trig with something exponential. However, there's a way to get around this problem. I'm going to go use a little bit of algebra, and I'm going to move this integral from the right side to the left side. I'm going to go and I'm going to add the integral of e to the x sine x dx to both sides. I've got the integral of e to the x sine x dx plus the integral of e to the x sine x dx. Well, that's going to give me two of those integrals over there. Normal algebra stuff, even though the variable is kind of like an integral. I'm going to say 2 times the integral of e to the x sine x dx equals, well, those pieces canceled over there. I'm going to get e to the x sine x minus e to the x cosine x. My original problem was for you to find the integral of e to the x sine x dx, and I'm almost there. I've got 2 times the integral of e to the x sine x dx, so I'm just going to go and I'm going to divide everything by 2. And I'm going to get the integral of e to the x sine x dx equals 1/2 e to the x sine x minus 1/2 e to the x cosine x. And you know what? There's one more thing I do need here. I do need to just stick a plus c on that answer. That's my integral. I wanted to show you one more, but I think I'm actually going to hold off till the next video to do one more of those. It's going to be the same idea, just a little bit messier. In the homework, I'm just going to give you a pretty straightforward cyclical integral. And again, you'll do one a little bit more involved next time.